Okay, I'm sure that's fine. All right, are we ready? So today we're going to learn how to start doing some calculations with gas laws. So we'll be able to quantify things like, if the temperature outside drops to like 20 degrees, how much will your tires shrink? How much will the pressure go down? You'll be able to calculate that just from this lesson. You'll be able to calculate things like, if the temperature of a hot air balloon, if the air inside a hot air balloon goes up by 100 degrees, then how much will the air expand? What would the air pressure be instead? We're able to do things like that. So today we're going to list different variables that we might use in gas law equations and identify their meanings and units. And then we're going to perform calculations with these variables. I'm using Boyle's law, Charles's law, and Gay-Lussac's gas laws. So gas properties can be modeled using math. These variables that we're going to look at are pretty self-explanatory just based off of these letters. But whenever you see these letters, this is what they mean. The capital V stands for the volume of the gas. So that's going to be units of like milliliters or liters, things like that most of the time. Capital T is going to be temperature of the gas. So in chemistry, we only use degrees Celsius or Kelvin. But with gas law equations, we have to only use Kelvin. It must always be in Kelvin. And that's just because we're not allowed to do things like divide by 0 or multiply by negative numbers to get weird results. Kelvin will never be 0 and it'll never be negative, so it works for our gas law expressions. This little n that we see here, this stands for number of moles of gas that we have. The capital P stands for the pressure of our gas. So remember, the units of pressure that we learned last time were things like kilopascals, atmospheres, millimeters of mercury, and torr. And this capital R we're going to use next lesson, but this is called the gas law constant. We don't have to worry about it for today. All right, so let's look at this first law together, Boyle's law. So what is Boyle's law? Well, Boyle was a scientist that did these experiments with pressure and volume. And he saw that, for example, if you were to compress this container, if you were to make this container get smaller and smaller, if you half the size of it, then it turns out the pressure doubled. If you made the size like a fourth of what it was before, then it turns out that the pressure was 4 times as much as it was before. So he noticed that there was a very direct relationship here. As one thing went down, the other went up. So this is what we call a inversely proportional relationship. So as pressure goes up, volume goes down. And why is this the case? Well, we touched upon it a little bit last lesson, but basically it's because if there's less space for the gas particles to bounce around in, the collisions against the walls of the container are going to be more frequent, which means we have more pressure. That's the scientific reasoning there. So the formula that we use to calculate this relationship is P1 times V1 is equal to P2 times V2. Okay, so what does this mean? Well, the pressure, the P1 and V1 stands for the pressure and the volume of the gas initially, and then the P2 and the V2 stands for the pressure and the volume of our gas sample after we change something about it. Did we change the volume? Did we change the pressure? We will have changed something. So we can say initial, what is it at first? And then final, what is it in the end? And then whenever we're looking at Boyle's law, we're going to say that temperature and number of moles of gas are held constant. We're not changing those. We're just changing 2 things at a time here. So let's look at an example of Boyle's law in action. A sample of oxygen gas occupies a volume of 250 milliliters at 740 torr of pressure. What volume will it occupy at 810 torr? All right, so since I know that it's talking about volume and pressure and then volume and pressure again, that's definitely going to be Boyle's law. So I can use this equation that I know from Boyle's law and just fill in things that I don't know about. So something that can help, that I'm not going to do every time, but if it helps you break up the problem just a little bit more, please go ahead and do it, is you can just list out every single variable and start thinking about what to plug into the equation before you actually do any math. So we can say, okay, P1, what's our initial pressure? Well, they told us 740 torr, so I could write that down. What's our initial volume? Well, they told us that too. It's going to be 250 milliliters of gas. What's our final pressure? They did tell us that as well. It looks like it says it's 810 torr. And what's our final volume? They're asking for it. We don't know. So you can say like question mark, you could write X, whatever you like. We don't know it. We need to solve for it. So we can go ahead and plug in all of these numbers that we got into this equation that we have and rewrite it. So instead of P1, V1, and P2, let's put in the numbers that we know about. So let's see, 740 torr times 250 milliliters is equal to 810 torr times some unknown volume. All right, so basically we're just going to be performing calculations with the numbers themselves. But I like to include units because I like to see them being canceled out. It's like, makes me happy. So when we're solving for V2, how do we get V2 all by itself?
You would divide
Exactly. So we would divide by 810 because right now it's being multiplied by 810. So we want to do the opposite of that. So let's divide that side by 810 torr. And that means let's divide the left side by 810 torr as well, which cancels out torr. And then that cancels out that whole 810 torr on the right side. And now we're left with V2 is equal to 740 times 250 milliliters divided by 810. So all we have to do is calculate that on the left side to get our answer. Okay, and that gets us something like 228. And what unit is left over here? Milliliters. So that makes sense because that's a unit of volume that we were using. So just to double check your work, it helps to kind of zoom out a bit and think about the relationship. It looks like the pressure went up a little bit. So I'm thinking the volume is supposed to go down a little bit. It looks like the volume started at 250 and ended up at 228. So that makes sense. The answer makes sense. So I'm at peace with it. All right. So let's move on to that next page and talk about, I think, Charles's law. What is Charles's law? Well, Charles did a lot of experiments with volume and temperature of a gas. For example, you can see on the right here, like we have this balloon, and if you put the balloon in ice water, it seems to shrivel up and shrink quite a bit. If you put it in boiling water, it expands quite a bit, like it might even pop because it's getting so inflated with air. Same amount of air molecules, but they're just moving around faster and taking up more space. So he noticed that as temperature goes up, volume goes up, or as temperature goes down, volume goes down. So that means that volume and temperature are directly proportional. They increase together and decrease together. The formula for this, how we show a directly proportional relationship, is normally it looks like a fraction. So we'll have like V1 over T1 is equal to V2 over T2. And I wouldn't be too scared of fractions because y'all are pretty good at that one math technique, just cross multiplying and dividing. You'll do that whenever you see fractions a lot like this. So whenever we're looking at Charles's law, we tend to keep pressure and number of moles of gas constant. We're assuming those don't really change. So let's look at an example of this. A sample of nitrogen gas occupies a volume of 250 milliliters at 25 degrees Celsius. What volume will it occupy at 95 degrees Celsius? Okay, so I do have all of these things here. And let's see, I know I'm going to use Charles's law because I'm talking about volume and temperature. And I can just kind of list out all of my variables. All right, so my initial volume is 250 milliliters. My initial temperature is 25 degrees Celsius. I don't know my final volume, unknown. It's asking for it, what volume? And then it says the second temperature is 95 degrees Celsius. Okay, so I know these are all like the values I'm going to plug in. Am I allowed to use these numbers as is? What do I have to change? There was this rule with Celsius. Am I allowed to use Celsius in these calculations? I have to change Celsius to Kelvin. So before you do any calculations with gas laws, you must change Celsius to Kelvin. And it's quite an easy conversion. What do we do to Celsius to turn it to Kelvin? Exactly. Let's add 273 to this. So note to self, must change Celsius to Kelvin. And then plus 273 is how we do it. So 25 plus 273 equals 298 Kelvin. And then 95 plus 273 is equal to 368 Kelvin. So these are numbers that we're allowed to use in our equation. We're allowed to keep whatever units of volume that we want, but temperature always has to be in Kelvin. Okay, let's go ahead and plug in these numbers and solve for our answer. So if we plug in the numbers into this equation, we get 250 milliliters over 298 Kelvin is equal to some unknown volume, V2, divided by 368 Kelvin. Okay, so how do we solve for this unknown volume, V2?
You would multiply by 300.
Yeah, so we could start like doing it step by step, multiplying both sides by 368. If you ever see a setup like this with fractions, y'all probably know you can just cross multiply and divide by the thing across from it. So you can multiply 250 by 368 and then divide by 298, and then you'll get your answer right away. So let's go ahead and do that. But if you prefer to do your math a different way, you'll probably get the right answer still, because everyone has their own interpretation of math. As long as it's correct, it's fine. And then we get something like 309 milliliters as our unit of volume here. Questions so far? All right. So the final scientist that we're going to talk about is Gay-Lussac. I don't know how to pronounce his name right. I think that's the most accurate I can get. I think he was a French chemist, but he did a lot of experiments with pressure and temperature. So you see these closed containers over here. You can just consider it like, let's say it's cold, not very scientific words, but cold, medium, and hot. Let's say that. And these are all just the same volume containers. But we can see here that there's these little arrows by the gas molecules. So we're going to say the arrows represent the speed of the gas molecules. So notice that when they're cold, they're moving kind of slowly. When they're kind of like medium temperature, they're moving a bit faster. And then when they're hot, they're moving really fast. So we have to think about, okay, why does temperature affect like the speed of the gas molecules? Well, temperature is speed of gas molecules. That's kind of the definition of temperature. But we have to think about what's happening with pressure. So pressure is caused by the collisions of the gas molecules against the walls of the container. We know that. If the gas molecules are moving faster, do you think they collide more forcefully? Yeah. So what do you think happens to the pressure as temperature goes up? There's harder, forceful, more collisions. And if there's more forceful collisions, what happens to pressure? It goes up or down? It goes up. So pressure increases as temperature increases. And then the opposite is also true. Pressure decreases as temperature decreases. So that tells us that pressure and temperature are directly proportional to each other. And we just explained why there. So the formula is very similar to the volume and temperature one, where let's go ahead and put temperature on the bottom and pressure on top. And then we have a second pressure on top and the second temperature on bottom there on the other side of the equation. And we're assuming that the volume and the number of moles of gas are held constant here. So let's look at an example of this. A sample of gas has a pressure of 75 kilopascals and 0 degrees Celsius. The pressure is increased to 125 kilopascals. What is the new temperature? Okay, so because we're talking about pressure and temperature, we know it's going to be using this equation with pressure and temperature. And we can just kind of plug in the things that we know about and then solve for whatever we don't know. So our initial pressure here, it looks like it's 75 kilopascals. Our initial temperature is 0 degrees Celsius, but we did say before that it should not be Celsius, it should be in Kelvin. So let's go ahead and add 273 to that. So we have 273 Kelvin there. Our second pressure is 125 kilopascals. And our temperature is currently unknown. Question mark. Okay, so let's plug in what we know and solve for the thing that we don't know about. 75 kilopascals over 273 Kelvin is equal to 125 kilopascals over who knows how much temperature. I don't know. Unknown temperature. Okay. So I mean, before we even solve the math, we can like just think, okay, if pressure is higher, do we think temperature is going to be higher or lower? Probably, temperature is going to go up as well. So higher pressure should mean higher temperature. Let's go ahead and do the same technique that we did before. You can just cross multiply and divide here. And that will give you the correct result. So cross multiply those numbers and then divide. Just make sure you're doing it in the correct direction here. So 273 times 125 divided by 75 gets you a final temperature of something. I'm getting like 455. And what are the units of my temperature here? This is in Kelvin. So if the question is specifically asking you for Celsius, you might have to do one more step where you convert it back to Celsius by subtracting 273. So you don't really have to do it unless it asks you to, but just to cover your bases, you can say, well, that's equivalent to 182 degrees Celsius, which is a bit hotter than we started out with. So that makes sense. Questions so far? All right, we do have just one more concept and example problem really quick on the next page. So all of these gas law relationships, they can actually be combined at once. Like what if we're changing more than one thing at once? So far we changed like maybe one pressure, one temperature, one volume. We kept everything else constant. But we're allowed to change multiple things and then compare, what's going to happen right after. So let's go ahead and do that. This is called the combined gas law. You can put all the gas laws together in like one equation to see what happens if you change multiple things. So the equation for this is just kind of plugging everything together here. We have P1 times V1 over T1 is equal to P2 times V2 over T2. And if you Google online, sometimes some people like to put moles of gas in there. They like to put N at the top. We're not going to really do that in this class, but just know that that is something that people can do. Okay. So just more variables. Make sure you don't get lost, but don't get overwhelmed. Just take it one step at a time. So let's look at an example of this. Find the volume of a gas at 0 degrees Celsius and 1 atmosphere pressure when 2 liters is collected at 745 millimeters of mercury and 25 degrees Celsius. All right, so I'm seeing a lot of things mentioned here, like at least all 3 variables before and after. So I think I'm going to use the combined gas law equation. P1 times V1 over T1 is equal to P2 times V2 over T2. And I could just list out all of my variables here. P1's equal to what? V1's equal to what? T1's equal to what? All right. And then we have P2, V2, and T2. All right. So a lot of things to plug in. Let's just take it step by step. Let's digest this problem and make sure everything is usable as is. Okay. First pressure here. Well, let's figure out what's going on. Find the volume of a gas. Find the volume of a gas at this temperature and this pressure. Okay, so that seems like maybe there's a final state there. And then when 2 liters is collected at this temperature and pressure, okay, this seems like the initial state to me. So just try to digest that question a bit. So it looks like the initial pressure is 745.0 millimeters of mercury. It looks like the initial volume is 2.00 liters. It looks like the initial temperature is 25.0 degrees Celsius. And then just going down, it looks like our final pressure is 1 atmosphere pressure. Our final volume is, I don't know, we're solving for that. And then our final temperature is 0 degrees Celsius. Okay, So let's look at our variables and make sure they make sense before we even do any math. All right. So I know, first of all, temperature has to be in Kelvin. So let's make sure that's in Kelvin first. I'm given degrees Celsius, so let's convert this to Kelvin. 25 degrees Celsius should be like what? 298 Kelvin, so plus 273. And then 0 degrees Celsius plus 273 should get us 273 Kelvin. Okay, is there anything else I should adjust here? Probably the pressure. I don't think we're allowed to use millimeters of mercury and atmospheres in the same problem. They should both be the same. So you can either convert everything to atmospheres or you can convert everything to millimeters of mercury. It's personal preference. You will get the same answer either way. Right now, I'm personally thinking, well, I already know 1 atmosphere pressure is equal to a certain number of millimeters of mercury. What is it equal to? 760 millimeters of mercury. So if you can do one conversion in your head off the top, just do that. Makes it a little easier. And these are numbers that we will use in our problem. I think that's pretty good. Okay, so let's plug those in and solve. First pressure is 745. I'm not going to write the units here because it's just a lot of mess. Times 2 divided by 298 is equal to 760 times unknown volume divided by 273. Okay, and you can solve this however you want. I know a lot of people start to get overwhelmed with like the algebraic manipulations. Like if I tell you, oh, we simply do 745 times 2 times 273 divided by 298 divided by 760. I realize I might lose some of y'all. So it's okay if you do it one step at a time. For example, we could just solve the left side and write the answer right there. Okay, so we could do 745 times 2 divided by 298, and that gets you like 5. And then we have, on the right side, we have 760 divided by 273, and that gets you like 2.78 times your second volume. Okay, so now that it looks a lot more simple, how do we solve that? I guess I could put 5.00. We could just divide both sides by 2.78. And then you should get your answer, getting the second volume, the second unknown volume, all by itself. So 5 divided by 2.78 gets us something like 1.80. And then what are my units of volume here? Liters. So don't leave that out. Don't leave the liters out. Jada, you have a question? Oh, okay. What questions do y'all have? That was the lesson. Now you can make calculations and predict gas law behavior. Just knowing some pressures, volumes, and temperatures. All right, you do have practices attached to the back of this. We will quiz at the start of next class. And I'll tell you, quiz probably be open note, open practice. So if you have nice notes in practice and you bring it to school, then you'll probably do well in the quiz. All right, I'll end this recording here. Watch it not be recording. Thanks for watching.